Okay, good morning. Welcome back to Mass 814, Algebraic Theory of Semigroups. So last discussion, we look at full transformation semigroup. I think the most important thing we did was the proof of the theorem, which is considered to be an analog of Cayley theorem in semigroup. Remember, Cayley theorem in group theory stated that every group is isomorphic to a group of permutation. And then this gives the group of permutations a universal property in the sense that it contains an isomorphic copy of every other group whatsoever. So something happened which we proved in the last class, that also every semigroup is isomorphic to a full transformation semigroup. That is a sub-semigroup of the full transformation semigroup. So which means the full transformation subsemigroup is also having a similar universal property of containing isomorphic copy of every semigroup. What I'm going to do now is to still tell you about some important classes of semigroups. The one we call regular semigroup. In fact, most of our discussion will be on regular semigroups. And then we'll also talk about some other classes of regular semigroups. That is semigroup of other important, like bands, we call them bands. And then there are other classes also, rectangular band. I think this is the one I'm going to mention. So I will start by defining what a regular semigroup is. So definition. So an element A of a semigroup S is called regular if there exists some other element, some B in S, such that A is equal to ABA. If you multiply A with B and A, you get A back. Then A is regular. Okay? Well, just to tell you what a regular element in a semigroup is. But we are going to look more deeper into these situations of regular elements, after I introduce the concept of Green's relation. So I will still come back to a discussion of regular elements, inverses, and regular semigroup, and so on. But I think for now, this is what I will just say. Maybe I will have to say that to define the inverse, actually, but before that, let me just define this. So if a semigroup, if every element of S is regular, then S is called a regular semigroup. Regular semigroup. Did you get this? The semigroup is regular if every element in the semigroup is regular. Otherwise, that semigroup is not regular. Are you following? Can you think of example of this kind of situation where not every element is regular? In fact, let us still look at the very simple example here. What are the regular elements? You can see one is a regular element there because I have something I can multiply here in the middle to get one back. What is that? Still one. I hope it's okay. Minus one is also regular because of what? You can still put something in between here to get minus 1, which is still minus 1. Minus 1. Okay? And these are the only regular element in this semigroup. Chris, is this okay? All right. So, and in this semigroup of integers, with respect to multiplication, these are the only regular elements. Well, no, not the only regular element, sorry. I think 0 also is a regular element. If you say 0 times 0, 0, you get 0. 0 also is a regular element. So you have 3 regular elements in this semigroup.
But if you pick any elements apart from 0,
yeah.
you put it at the middle, you still get 0.
Yeah, in fact, you don't have to use 0 in the middle. You have to use any n. Any integer you put in the middle. For 0, you always get regular element. You get 0 back. So 0 is also regular. I hope it's okay.
Yes.
So this is what we call regular. Regular element of the semigroup. So if it happens that all the elements in a semigroup are regular, then that semigroup is a regular semigroup. Is that okay? But this particular one is not regular. So this is an example of a semigroup that is not regular. Don't say irregular. So irregular may mean something else. Okay, but say it is not regular. Okay. It's okay. All element, if the semigroup is already a group, then every element is regular. If you take a group, it's a semigroup, then every element is regular. If I take any A, I can always find A inverse to be put in between here. So that at the end of the day, I arrive at A. In the group. Every group whatsoever. If the semigroup is already a group, always this is doable. I hope it's okay. Or if it is a 0 group, a semigroup that is a 0 group, this is also doable, always. Like if you take the semigroup of rational numbers with multiplication, is that okay? You take any rational number p by q, you can always get what? Q over p, such that this will give you what? P over q. Always. And if the number is 0, then anything you put in between, you always get 0. So for any non-zero, you get the inverse of it, and it gets you there. And if it is 0, you always get it. So if the semigroup is a 0 group, then every element is regular. Is that okay? So you have example of semigroups that are regular, and some semigroups are not regular, because some elements are not necessarily regular in a semigroup. Okay? So, I already defined what we mean by what? Idempotent. So still I'm defining what we mean by the inverse, but we are coming back to that. So if S is a regular semigroup, and A is an element in S, then an element B in S is called the inverse of A if A, B, A equal to A, and B, A, B equal to B. In fact, this condition of inverse is equivalent to the condition of regularity. Because if an element has inverse, by satisfying this condition, it means it's regular. And whenever an element satisfies this condition, it will definitely have inverse. Are you following? So what I'm trying to say is that we can prove a lemma here 1.7, that in a semi-group, in fact, you don't have to assume regularity here, but because I want to say that, so in fact, this is always true in any semi-group. If there is an element B such that this is happening, then B is the inverse of A. But A must be regular. I hope it's okay. So in a semi-group, S, an element A in S has an inverse if and only if it is regular. It's only regular element that can possess inverse. Are you following? Only regular elements can possess inverses in a semigroup. Elements that are not regular cannot have inverse. This is what this lemma is trying to inform us. That if an element has an inverse, then it must be regular. And if it is regular, it must have an inverse. So this is what the lemma is saying. You can prove it. It's not difficult, but let me just establish it for you. Or do you want me to leave it as an exercise? Huh? Yeah.
Do we need to write the second condition?
Which second condition? Yeah, for the definition of inverse, you must write the second condition.
In that happens, it means A is also the inverse of B.
Yeah, that's correct.
B is also.
That is correct. This definition is symmetric in nature. If B is the inverse of A, then A is the inverse of B also. So yeah, this is the same with even group theory. When you are defining inverse for A, it is some element B such that A, B equal to identity and B, A equal to identity. But that definition automatically implies that A is also the inverse of B. I hope it's okay. So the definition is already symmetric in its nature. So it's already pronouncing that A is the inverse of B. So if B is an inverse, well, an inverse, because this situation, inverses in this setting may not be unique. You can have so many inverses for a particular element. We will see all this. So in fact, this is why I'm saying all this, and just to point out to you that semigroup is entirely different from what you are familiar with in group theory. You know, in group theory, if every element has inverse and the inverse is one and only one, unique. But in semigroup theory, an element can have so many inverses. In fact, there are semigroup where every element is the inverse of every other element. Such semigroup are called rectangular band, or band. Even in band, yeah, rectangular band, yes, rectangular band. Thank you. So if B is an inverse of A, then it is immediate. Yeah, because it means this happened. So this first equation is already saying A is regular. Then it is immediate that what? A is regular. Nothing to show. In the converse, if A is regular, okay, then, then there exists some elements. Is it B? Better you take X. X in S, such that AXA is equal to A. Now, look for the inverse of A. Meaning, look for an element B that will satisfy this equation. These two equations. This is what you will do. Okay? Now, choose B to be equal to XAX in the semigroup. Because this is an element of the semigroup, so this product is existing there inside the semigroup. Okay? Then What is ABA? ABA will be AXA, like this. We can associate is AXA, yeah, XA, yeah, correct. Okay, but this is A,
This is A.
so it is AXA, and that is B. No, yeah, that is A again.
That is A.
It's A again. So ABA is A. So which means this first part of the equation is proved. You cannot conclude that B is the inverse unless you prove the second part of the definition of inverse. You know, this one is only showing that A is regular, but then this must be satisfied. So it's like saying A is made regular by B and B is made regular by A. Are you following? So you have to show that B is also made regular by A. So you have to do the other one. So you have to establish this. So, and BAB should be equal to XAX for the B. So this is what you choose to be. A in the middle here and XAX. And that would be equal to, so you can still play around with the bracket. And you see the advantage of working in a semigroup. You can use bracket the way you like. Okay? So, and XAX. And this is what? This is A. So AX, is that okay? AX. That is okay, huh?
Okay.
But this is what? This is A. And you get B. And so B is an inverse of A. So that is the proof. It's not difficult, it's just 2 lines. Well, I mean, 2 pages, 1 page. It's not up to a page. Pages of the board. Okay? Thank you. Yeah. Yeah. Okay, good question. We are defining inverse without making reference to identity. Well, we are defining inverse in a semigroup. A semigroup is not necessarily with identity. Okay, so in case there is no identity, we have to formulate the definition of the inverse in a way that identity is not mentioned. Yeah. But you know, in group theory, an element is the inverse if what? A, B is equal to identity. But isn't that the same as saying A, B, A equal to A? Because this is identity multiplied by A that gives rise to A. And also B, A equal to identity. But isn't that the same as saying A, B, B, A, B, A, B equal to B? Distance. This terms A give us identity and then giving rise to B. So we better pronounce without making reference to the identity. The 2 equations defining inverse in group theory that made reference to the identity are the ones we are still mentioning here. But we don't want to mention the identity because we may not have identity in our semigroup. Did you get this? That's just a clever way of doing it without having to mention identity in case there is no identity in your semigroup. But this definition is more general now. It's more general than that of inverse in what? In semigroup, in group theory. That is why sometimes it's called generalized inverse and not inverse. But this is the terminology. We just say inverse in a semigroup. And elements doing this in a semigroup are not necessarily unique. Yeah. They are not necessarily unique. We will see why they may not be unique later on. Because these inverses are so when you multiply an element with its inverse in group theory, you get what? Identity. Now, if you multiply with the inverse now, you get what? You get the element?
You get the inverse.
You get the inverse? No, no,
You
no.
say equal multiply
If B is the inverse of A, so what is A times B
the identity
and B times A?
is one. A times this one is the identity element.
But you may not have identity in the semigroup. So if the semigroup has no identity, there is no way you can hit identity by multiplying elements because it's not there already. So what do you get? That identity, when you are looking at group as a semigroup, that identity is an idempotent. It's the only element that multiplies itself to get the element back. So you see the identity in group as an idempotent. But in semigroup, there are so many idempotents. So if you multiply an element with its inverse, instead of getting identity, what you get is an idempotent. Okay? All right. This is good, cool? So let us do that. So not that, yeah, so that means you can't speak of inverses in a semigroup where there are no idempotent. So anytime there are inverses, you must have idempotent. I don't know whether you understand what I mean. That is, if you have inverses in a semigroup, idempotent must exist. Meaning, if you multiply an element with its inverse, you get an idempotent. So that is if A is a regular element. So yeah, it's a remark actually. It's a remark that if A is a regular element of a semigroup S, then with X in, or let me say, yeah, X in S such that AXA equal to A, then both AX and XA are idempotent elements. Idempotent elements. It's not difficult to see. In fact, you can just square it. If you want to check whether an element is idempotent, just square it. That's all. So if you square, you get what? AX. But AS means what? This is X, this is A, that is A, that is AX. Because the first group of 3 is A. And if you have AX square, it is what? XA. But this last group is A. So both AX and XA are idempotent. So what this remark is saying is that in a semigroup where there are regular elements, idempotent must exist. In fact, idempotent are automatically regular elements because if E is an idempotent, then E square equal to E, and so therefore it means E cube will still be what? E. Is that okay? So that means you are saying E times E equal to E, which means it is acting like the inverse of itself. So idempotent are self-inverses. I hope it's okay. So they are the ones behaving like identity in group. In group, the only idempotent is the identity. But in semigroup, you may not have idempotent identity, but there are elements behaving like identity of that particular system, and those are the idempotent elements. And these are more powerful than the identity if they exist because they can collaborate together to generate the entire system. Unlike in group, identity doesn't generate anything. Identity alone, if you keep on multiplying identity, you just keep on getting the identity back. But for idempotent, in their own right, if you take a particular idempotent and keep on multiplying, it will just behave like the way identity is behaving because E square is E E cube is E to power 4. You don't get anything new. Are you following? But if they collaborate together, if you have more than one of them, they can collaborate together and produce new elements. So if you take one idempotent and multiply with another idempotent, you get something new. So idempotent are very important in the system, and we will see the role of idempotent a lot when we come to talk about product of idempotent, mostly in transformation semigroup. So let me give you a definition now, some special class of regular semigroup. A semigroup S is called a band if all its elements are idempotent. So everything inside it is an idempotent. Idempotent. So a semigroup consisting of all idempotent is called a band. Did you get this? If every element in the semigroup is an idempotent, then that semigroup is a band. Okay? It's a band. I think this is clear. There's nothing to. Example of a band? Well, well, I don't know. Maybe I will. Like, if you are in the semigroup of, you take this semigroup. I don't know. I have to talk about something which I haven't mentioned before. But let's say you take partial maps. Maybe I will tell you later on. Okay, but the definition is clear because I haven't prepared to present a concrete example of this. This notion is very clear, but that is if every element in the semigroup is an idempotent, then the semigroup is a band. You remember my soft semigroups? We said this is a soft semigroup. Did you remember this? You remember this one? Yeah, every element is, but these are singletons. But you can have semigroup with so many elements, and they are what? Idempotent. All the elements are idempotent. Yeah. Like if you take the semigroup of partial identities, so let's take partial mappings. Like if you take the empty map, that is, nothing is mapped to anything. Partial mapping means taking subset to a subset. So like 1, 1. So you are talking about a set of two elements. One is mapped 1 and 2 is left unmapped. And then like you take 2, 2. All these are partial identities, identity mappings. And then you take 1, 2, 1, 2. This is like the identity mapping. This system is a semigroup. All the elements are idempotent. You know, all of the elements here are idempotent. And if you multiply any two, the result is still an idempotent. When you check this system, you see that it's close, it's associative with respect to composition of mappings. So this is a concrete example of a band semigroup where all the idempotent are. All the elements are idempotent. So, but now, if every element is an idempotent, if you take any A in the semigroup, A square is A. Because everything is an idempotent in a band. But if A square is A, it means A cube will be equal to A. Meaning what? Every element is regular. Yeah, because A cube means what? A, and I get something in the middle that produce A. So a band is a special example of a regular semigroup. That is a regular semigroup for which all the elements are idempotent. So every band is also a regular semigroup, but not all regular semigroup are bands. Like the full transformation semigroup is a regular semigroup. We'll prove this fact later on. But not all the elements inside are idempotent elements. I hope it's okay. Full transformation semigroup is a regular semigroup, but not a band. Okay? So let us look at another class of semigroups, which we call rectangular band. The definition. A semigroup S is called a rectangular band. Band if what? For all A, B in S, A, B, A equal to A. How is this definition different from what we call regular semigroup? Can somebody tell me? How is it any different from what we call regular semigroup? Remember our definition of regular semigroup? That every element is regular. Yeah, it means every element is regular. For all A equal to A. Yeah. But regular semigroup, ABA may not be A for all the elements. If you can find only one element of the semigroup, X, so that AXA equal to A, then it is regular. If for all A there is some element that this will be equal to A, then it is okay. It's regular. But for rectangular band, for every ABA must be A for all other elements of the semigroup, even including the A itself. I hope it's okay. That is a rectangular band. A rectangular band is a regular semigroup for which every element is made regular with respect to every other element. But you know now, since we say ABA equal to A, it means BAB will also be equal to B. Since this, are you following? Which means every element is the inverse of every other element in a rectangular band. So you see, inverses are not unique automatically in semigroup, not necessarily unique. I hope it's okay. So every element is regular with respect to every other element, because this statement is pronouncing that B is an inverse of A and A is an inverse of B. Are you following? So this is a semigroup where any element you pick will be the inverse of everything, is the inverse of everything else. I hope it's okay. It's a very interesting situation. Okay? In fact, we have a very nice characterization, because you wonder why band. But why do we say band? What do we call band? It's a semigroup for which all the elements are idempotent. So having to call this band, is signifying that elements here are also idempotent. Are you following? It means every element is an idempotent, since we see the name band. But why rectangular? Okay, maybe we will justify that in our theorem. 1.8. Is that okay? Yeah. So a semigroup, well, let S be a semigroup. Then the following are equivalent. Equivalent. These following statements are equivalent. Number one, S is a rectangular band. Number 2, so I'm just giving you different other ways of what? Defining a rectangular band. I hope it's okay. If you say the following statement are equivalent, to say that it is a rectangular band is the same thing as saying every element in S is an idempotent, and that for all A, B, C, A, B, C in S, the equation A, B, the product, if you multiply A, B, C, you get AC. Meaning every element of the semigroup is acting like a middle identity with respect to every other element. Are you following? So if you just see a product, you can remove the middle ones, the middle ones. I hope it's okay. In that semigroup. So if everything is an idempotent, okay, what happened?